last lecture, we learned about the weak focusing. We derived an equation of motion, and this equation of motion was for the particles motion when there is a dipolar magnetic field having some gradient in it. And this combination of dipolar magnetic field and gradient leads to weak focusing. Now there are and also we learned about the geometric focusing, in which shape of the magnet, which is known as sector dipole magnet, due to virtue of its geometry, it focuses in the horizontal plane. There are another types of focusing also available for the charged particle motion, and those are strong focusing and edge focusing. And on the basis of strong focusing, there is a principle, namely alternate gradient principle, in short AG principle, which is used to make charged particle optics in synchrotron and transfer lens. So we will learn these things in present lecture. Now here we recall the focusing of light using the thin convex lens. So just I draw a convex lens, which you have learned during your school courses, that this is a convex lens and this is the optic axis, and light ray when passes through this lens, it bends the light rays to have a focus on a point. This is the focal point. So it has some bending here, theta, by which light ray bends during the passage of the convex lens. So we also have to have such kind of bending for charged particles if we want to focus these charged particle rays. So how this can be achieved? We will see this now. In charged particle, definitely the control of trajectories is using the magnetic field. And in magnetic field, if charged particle passes, the radius of curvature is this. We have seen this formula again and again, that radius of curvature is directly proportional to P and inversely proportional to magnetic field B. Now if there is a charged particle and if it is passing through a region where magnetic field B is applied, then we can calculate what is the bending. And that bending, you can say that this is the bending by d theta, and this is the radius of curvature r. So d theta will be q by p b dl. This is just dl by r, and r is placed from here. So in this case, the total bending of the charged particle trajectory will be q by p and integration of b dl. So this is the angle made by a trajectory under the magnetic field of the given length. It is the magnetic field which we use for bending the particle trajectory, and this is the length over which magnetic field is applied. Length over which magnetic field is applied. B is applied. So you can see here that alone B is not enough to decide the charged particle trajectories or angle in the charged particle trajectory, rather than the combination of the magnetic field and over the length on which it is applied. That is much more important. Means combination of magnetic field and length. It is useful rather than only B. So now we see the basic mechanism of focusing. How we can achieve the focusing. So suppose this is the optic axis in red color, and a particle is coming on this trajectory, and this is the magnetic element which we want to use as a lens. Magnetic element. When it passes through this magnetic element, the magnetic field and length of this element generates a bending theta 1 in the trajectory, and trajectory passes through this point. Here the deviation in the particle trajectory from the design trajectory is x1. So if this happens for all the trajectories, then we say this magnetic element is capable of focusing the charged particle rays. So we draw another trajectory also which has larger deviation x2 than the previous trajectory. Then it has larger bending angle to reach the same focus point. If we draw another trajectory having opposite displacement, means displacement in the opposite direction to the design axis, then again it has the opposite angle due to sine in the sine. Means if we say that sine of these angles are minus, then sine of this angle is plus. So now we can see by these trajectories that theta is directly proportional to x. As x increases, the required theta is also increases to send the trajectories on the focus point. And if x changes its sign, theta should also changes its sign. Therefore, now we have seen in the previous slide that theta is directly proportional to BDL. D theta is directly proportional to BDL. Means this theta means BDL. It should be directly proportional to x. Then focusing can occur. So if this combination we are able to generate proportional to x, then that kind of magnetic field will focus the charged particle. In geometric focusing, B was fixed because that is the dipole magnet. So that was constant over the space. However, the length which the trajectory passes through the magnetic field has different for different initial displacement, and that different dl or l leads to focusing. And in the magnet, dipole magnet, if you introduce the gradient, then bending as well as focusing is achieved. That is known as weak focusing, and in that case field index must be between the 0 and 1 for stable motion in both the planes. Can we separate the bending and focusing? Can we make a magnet which is having only gradient and no dipolar component? In that case, no bending of the design path will be there because dipolar magnetic field is absent and there is only gradient, so focusing can occur. This type of magnet will behave exactly the lens as of the light optics. So answer is yes, we can do that. If we can generate such kind of magnetic field in which vertical component of the magnetic field increases with displacement x from the design axis and the horizontal component of the magnetic field increases with the vertical displacement, then this kind of magnet can be used exactly similar to the convex lens in the optics or concave lens in the optics. Now you can see here on the design axis we have x is equal to 0 and y is equal to 0. These are the coordinates on the design axis because on design axis itself defines the origin. So x is equal to 0, y is equal to 0. This gives bx is equal to 0 and by is equal to 0 for this case. And bx is equal to 0 and by is equal to 0 means there is no magnetic field on the design path. Means design path traverses this magnet without getting affected. There is no effect of this magnet on the design trajectory. And this is the case similar to the light optics, that optic axis does not change when it passes through the convex lens or concave lens. And as x becomes non-zero or y becomes non-zero, there is finite magnetic field. And this magnetic field is used to bend the particle trajectories which are deviated from the design axis, and this angle of the deviated trajectory leads to the focusing. This kind of magnet is known as a quadrupole magnet because this field can be generated if we have 4 poles rather than 2 poles. Now how these 4 poles will be arranged, we will see it. Now by as a gx which was written. So this is the graph showing the variation of by with x. This is a simple straight line having some inclination with x-axis, and this inclination defines the gradient. What is the gradient g? Now you can see that as x increases here, x is increasing here, the magnetic field also increases. Means the applied force by the magnetic field on the charged particle will also increase. So as we go further and further from the design axis, this is the design axis, which is x is equal to 0, y is equal to 0 origin. Here is the design axis coming out of the screen, and if particle is deviated along the x-axis, the more deviated particle feel more force, means more bending, and it is the desired characteristic of the focusing edge. We have seen that if x is more, theta should be more, and if x is negative, here is x is negative and here x is positive. So in the case of negative, because by is also has changed its sign, so force will also change its sign, and it will be in the reverse direction of this direction. So now again, if particle is deviated towards negative x, it will get a force towards the positive x, and if particle is deviated in the positive x, it will get a force in the negative x. So overall, all the particles will feel a force which will send those particles towards the design axis. It means this is a kind of focusing. We are trying to confine the particles towards the design trajectory. Now, how the 4 poles are arranged? These 4 poles are arranged in this manner. This is a north pole, this is a south pole, this is again a north pole, and this is a south pole. These 4 poles make a quadrupole magnet. This is the pole phase profile. Now, like the conductor, in the conductor the electric field line always meets at right angle. In a ferromagnet surface, the magnetic field lines meet at right angle. So these are the magnetic field line which emerges from the north pole to south pole, and due to symmetry, here it is the north pole at this distance, and similarly here is the north pole at this distance, here south pole on the same distance, and south pole tip here is also on the same distance. So due to this symmetry, magnetic field will be 0 at the center, which is the desired characteristic of a lens. And as we go away from the design trajectory, you can see the gap between the pole faces is reducing, and this reduced pole gap generates a higher magnetic field, and higher magnetic field means more force. So larger deviation in the particle coordinate will give a larger kick by this magnet. Now you can see here, if we take 4 points, say this is the point number 1, this is point number 2, and this is point number 3, and this is point number 4. So point 1 and 2 are having deviation along the x-axis, while point 3 and 4 are having displacement along the y-axis. Now at this point, the magnetic field line is in just this direction, that is the tangent at this location on the magnetic field lines. Here the tangent is in this direction, so magnetic field is in this direction. You can see that when x is positive, magnetic field is in the opposite direction with the case of when x is negative. The similar is the case for y-axis, that on the positive y-axis and negative y-axis, the magnetic fields are in the opposite direction. Now if a particle comes here, suppose, and particle comes here on the point 3 and point 4, you can say if particle is coming, it is coming out of the screen, and magnetic field is in this direction. So force will be V cross B. So V is outside the screen, B is in this direction, so force will be in this direction. Similarly, here, because the magnetic field has the reverse direction than this place, so force will also have reverse sign in the direction, so force will be in this direction. So force on a positively charged particle which is coming outside will be in this direction on the vertical axis. So force is towards the design axis. Now suppose the deviation in the horizontal axis. Now you can see if you are taking the positive charged particle which is coming outside, similar to the case of point 3 and 4, you will see that the direction of force will be away from the axis. So this is not desired here. Means this type of quadrupole magnet is focusing in the vertical plane while it is defocusing in the horizontal plane. But we have to live with it. Actually, Maxwell's equations compels us to have By is equal to Gx and Bx is equal to Gy. And due to this, we have focusing either in horizontal plane or in vertical plane. In the other plane, there will be always defocusing. So suppose if we swap the poles, means north is swept by the south and south is swept by the north, means we have rotated the quadrupole magnet by 90 degrees, then the focusing will occur in the horizontal plane and defocusing in the vertical plane. Means if we consider a single plane and we place two quadrupoles just rotated by 90 degrees, then first quadrupole if it is focusing, then second quadrupole will be defocusing. Means we have a convex and concave lens combination. Similarly will be the case for the other plane. Here concave and convex combination will be there. So using these two combination, we can always make focusing in both the planes. Now, what is the focal length of this lens? This is the particle trajectory which is coming. When it passes through this magnetic field, it generates a bending angle theta and particle trajectory crosses from this point. So for obtaining the focal length, we have to take initial condition in which x prime is 0. Means this trajectory is making 0 angle with respect to design axis. Means it is coming parallel to the design axis and it has certain deviation x. And this is from where it cuts or it crosses the design path, it is the focal length. So due to simple trigonometry, we can obtain that f is equal to minus x by tan theta. Here I am taking this sign as a minus. And in paraxial approximation, where theta is small, we can always have tan theta is approximately theta. And this approximation is again used here. So our focal length is x by theta x. Now from previous slides, we can put the value of theta x in terms of B and L. Now here theta x will be q by p integration of by dl. And by for the quadrupole magnet has gx. So in place of by we can put gx. So this will be gx dl, and g, it is the gradient. So gradient will be constant for a given quadrupole magnet. We have seen that in our this slide that this gradient is constant for a given quadrupole magnet because this is a straight line. So gradient will not change, only magnetic field will change. So gradient is constant in the quadrupole magnet. So this gradient is constant. We can take it outside the integration. So this integration will be q by p g integration x dl. Now if we take very small length for the quadrupole magnet, means dl is very small, means we are talking about the thin lens approximation, means dl tends to 0. This is the thin lens approximation. In thin lens approximation, we can assume that x remains constant inside the magnet. Just you can see that this is a delta function where the magnetic field appears. So just before the magnet and after the magnet, x doesn't change. Only there is a change in the x prime, which was 0 earlier before the magnet. It changed suddenly after the magnet and has theta x, minus theta x in this case. So x can also be taken outside the integration. So this integration will become q by p gx integration dl, and dl is just the integrated length of the quadrupole. So this will be q g by p xl, and this quantity gradient normalized by the momentum and charge is known as normalized quadrupole strength K. So quadrupole's bending is equal to KXL. We say this is a quadrupolar kick. When kick is proportional to x, here we can say theta x is proportional to x, L and K are constant for a given quadrupole. So as x changes, theta also changes. So theta is directly proportional to x. In case of dipole magnet, this theta was independent of x. So this kind of kick is known as quadrupolar kick. And by comparing these two equations, this equation and this equation, we can say that focal length is just minus 1 by KL. Minus focal length is for focusing. For a diverging lens or concave type lens, this will be positive. So you can say a equation here, trajectory here, after a defocusing quadrupole, this trajectory goes away from the design axis, and in this case theta x is positive. This is positive. That's why focal length is also defined as positive in the diverging lens. Now suppose we want focusing in both the planes simultaneously. One quadrupole, it is focusing in one plane, then it will be focusing in the another plane. So for overall focusing in both the planes, we at least require two quadrupole magnets. So in any optics of charged particles, you will always see that at least there are two quadrupole magnets. In two quadrupole magnets in one plane, if it is focusing and defocusing combination, so for the other plane it will be defocusing and focusing combination. So by properly choosing the strength of these two quadrupole magnets and the distance between these two quadrupole magnets, you can see that these both trajectories can be focused. Means in both the planes we can get focusing. And recall your lens making formula. So this is the overall focal length of two lenses combination, that is 1 by f1, 1 by f2 minus d by f1 f2. F1 is the focal length of the first lens, f2 sorry it should be 2. F2 is the focal length of second lens, and d is the distance between these lenses. So this is also true in this case also. So you can always calculate the focal length of the combination of two quadrupole using this formula. Remember, this is valid only when we are using thin lens approximation. If quadrupole is not thin, then we have to calculate explicitly what should be the x and x prime at the exit of the quadrupole magnet, and what will be the effective focal length of that combination. We will learn these things when the quadrupole is not thin in the next lecture.